He is currently he is currently an assistant professor at the U of R since July of 2025. He received his PhD in astronomy at the University of Hawaii, where his thesis was the discovery and characteristics of giant planets and brown dwarfs on wide orbits. After his PhD, he did a postdoctoral research fellowship at the University of Texas at Austin, where he was a NASA Sagan Fellow. He was awarded telescope time on JWST, HST, Keck-2, as well as a number of other major telescopes. He's mentored numerous students. He has a total of 64 publications, of which he was first a corresponding author on 16, a second or third author on 6, and co-author on an additional 42. And we really welcome him here. Thank you very much. His talk is going to be on New Worlds Beyond Our Solar System. So I'm going to stop sharing.
Going to share. Right.
Thank you. Thank you. All right.
Yes.
Thank you.
Okay. Does the microphone work well? Okay, cool. Hello, everyone. I'm ZJ. Thank you for your introduction. I'm an astronomer from working at the University of Rochester, so it's pretty nearby. And to be honest, I have a 14-month-old daughter, and at this time every day, basically that's when my whole family has already kind of fallen asleep. So if any part of my talk sounds a little bit like a bedtime storytelling, probably that's why. But anyway, I'm really excited to be here. It's the first time for me to make a trip to RIT, although we're pretty close. And I'm really excited to talk about my favorite topic, the new worlds beyond our solar system. And I bet all of those new worlds must be way more awake than I am at this hour. So speaking of the solar system, we know we're pretty familiar with it. It's our home. We have the sun at the center, and we have 8 planets. As we can see, they have different sizes, they have different masses, they have different distances from our sun. So in order to quantify their properties, as astronomers, what we typically do is to place these solar system planets into a certain diagram. So this is a pretty kind of very common diagram that everyone who study exoplanets will kind of show in their talks. So this diagram, the x-axis is orbital semi-major axis. So this describes how far away the planet is from the sun or from the host stars of other planets, right? And the y-axis is the mass of the planet. So all of the 8 solar system planets are plotted here. So you can see their masses really span several orders of magnitudes because the y-axis and both axes here are plotted in log scale. So every time we see this kind of system, probably some people will have questions. Is it normal for a planetary system to really host 8 planets? And is it normal to have planets that have similar sizes and masses as Earth or Jupiter? How unique our solar system is? And also another kind of key question that we're kind of interested is, are we alone? So in order to kind of pursue all of these kind of questions, astronomers have tried to explore and find new exoplanets beyond the solar system. So over the past 30 years, we have been finding a lot of new things, and I will show that in the movie. So the early kind of discoveries were made somewhere 1995-ish, and since then, we have explosion of new exoplanet discovery each year. So at the end of year 2025, all of the kind of white circles mark the exoplanets that we have confirmed and discovered to date. So we can see these planets, again, they really span several orders of magnitudes in terms of masses and their orbital semi-major axis. And now, in this diagram, we're showing all of the exoplanets that we have discovered so far. And as I mentioned, all of these exoplanet discoveries really span several orders of magnitudes in terms of their masses and their orbital semi-major axis. So that also means this exoplanet population demonstrate like a strong diversity. So there are many different worlds that are kind of different from the world in the solar system. So here I will just show some examples. So one of that is the planet called Kelt 9b. If we just look at a planet that is really kind of close to their host star, around like 0.2 AU, 0.2 times the Earth's sun distance, and the mass is about Jupiter mass, right? And this planet is huge, but in the meanwhile, it is so close to its host star. So at the end of the day, the planet receives a lot of radiation from the star that makes the planet super, super hot. So we call this planet as like a lava world because there may be some kind of lava flows on the surface of this planet. Second example is like when we just look down a little bit, like to a planet that have slightly lower mass, but with sort of similar orbital symmetry axis. And this is one of the most famous exoplanets called K2-18b. And this is something that we call as Haitian world. So I don't know if any of you know what is a Haitian world here. This is really like a make-up word here. It's not a true word, but rather what happens here is like for this exoplanet, what we believe the planets might have is like it probably have some kind of water ocean like on the surface, but in the meanwhile, it is dominated by some kind of thick, heavy hydrogen atmosphere. So combining hydrogen and ocean, we get like Haitian. Right. So this is kind of the word that people use to describe a kind of exoplanet or a world that may be composed of both hydrogen and water ocean. So whether this is true or not, we don't know. So this is just one of the models that can explain the observed properties of these exoplanets. So studying this Haitian world is one of the top kind of priorities right now in the exoplanet community. We try to get more data in order to really answer this question, whether there are more Haitian worlds over there. So both of these planets are really close to their host star, and we can probably move toward the like wider orbits a little bit. So this planet is called Coconus 2b. So this is what I discovered a few years ago, and I will talk more about it later. So as we can see, this planet is like has several Jupiter masses. It is also very far away from its host star, right? If you read the x-axis, it's about like 6,000 AU. So how this planet resides on this kind of wide orbit? So this is a question that I'm kind of interested in answering right now. And given this kind of wide orbit, we can imagine this exoplanet receives almost no radiation from its host star. So it's probably like a frigid world, right? Very cold. So these are the three examples. But in principle, we can see like there are a bunch of like nice pictures about all of the exoplanets we have found so far. These are the artist's impression, definitely not the real data. But we can see like, again, they have a huge range in terms of mass and sizes. So now we have talked about the exoplanets with different masses, but do any of you know like what is the maximum mass of an exoplanet? What's it? 0.08? Exactly. Yeah. That's. I cannot imagine like you know the answer about that. So it's about like 80, like 0.08 solar mass, about like 80 Jupiter mass or 70 Jupiter mass. Like there's a certain range that is called hydrogen burning limit. So we can imagine like for the exoplanets, if we think about the planets with larger and larger mass, there's a certain point that like it does not qualify a planet anymore, right? Because when it's so massive, it can burn the hydrogen in their cores. So when they burn hydrogen in their cores, they're named as stars by definition. So there's some kind of nuclear fusion that is happening in the stars. But for the exoplanets, the kind of the fact is like we still have no consensus in terms of what is the true maximum mass for the exoplanets. So we know that they should be definitely below 70, but sometimes people adopt the IAU suggestion. The IAU is the International Astronomical Union. So they give a suggestion to say like, okay, so 13 Jupiter mass is what we can typically use to define an exoplanet. So why 13 Jupiter mass here? So the 13 joule per mass basically corresponds to the deuterium burning limit. So they are kind of trying to find a burning limit for a certain kind of atom to make this kind of definition. But this kind of definition for the exoplanets is kind of something that is under a great debate right now in our community, because the deuterium burning limit says nothing about how the planet forms, right? In principle, the planets and stars form in different ways. So stars form from a collapse of large molecular clouds. And for exoplanets, we believe that these planets can form either through something that we call core accretion. So it's like you just have a lot of rocks, they just grow together, they stick to each other, and then they start to accrete some gas, they grow up. So this is like a bottom-up way to grow an exoplanet. So ideally, we want to find a way to define a maximum mass for the exoplanet so that we can tell above this mass, the objects likely form as stars, and below this mass, the objects likely form as exoplanets. So the formation-based boundary, mass boundary, will be more physical in terms of defining what is the maximum mass for the exoplanets. But this is still something that we're kind of exploring right now. We don't have a solid answer as yet. Because we know for the 13 joule per mass, it's not always true. We find large exoplanets, right? The one that I showed, the diagram, we have exoplanets that are more massive than 10 joule per mass. Several 10 joule per mass, they orbit their own sun. So it's kind of not I think for our kind of astronomy or exoplanet community, we're not all very happy to use this definition at the moment. And probably you will think about okay, so now you say exoplanets based on the IAU definition is below 13 joule per mass, and stars is above hydrogen burning limit. But what about the objects that are in between? What about the objects with masses below 70 joule per mass? Do anyone know what they are? Yeah, so these objects are called brown dwarfs. So by definition, brown dwarfs are kind of objects that form similar as stars. So they also form from a collapse of large molecular clouds, but the thing is they form from a cloud that is not massive enough. And therefore, at the end of the day, they cannot grow up to a higher mass to burn the hydrogen. So that means they cannot burn hydrogen in their cores. So they are not stars in this way. But they form in a similar way as stars. And based on the theories of star formation, we can form a lot of things down to a mass of 3 joule per mass. So that means for the brown dwarf, the mass range is pretty wide. It ranges from about 3 joule per mass up to 70 joule per mass. So by definition, you can imagine some people call brown dwarfs as failed stars. So the reason they call them as failed stars is because they're not massive enough to burn the hydrogen. So they are not massive enough to be qualified as a star, and therefore they're called a failed stars. But as people who study brown dwarfs on a daily basis, including me, we definitely don't want to do the science on the failures, right? So there are some kind of jokes that some of my colleagues call this as overexcited planets, which is interesting. And also, right now, if you take a look at the mass range between brown dwarfs and extrasolar planets, you can instantly find there are some kind of tricky things. So the two types of objects, they form likely from different ways. So brown dwarfs form like stars, exoplanets form like planets, right? Core accretion, bottom up. But there's a strong overlap in terms of mass. So if you have a 10 joule per mass object, should we call them as a brown dwarf or should we call them as an exoplanet? So again, this is something that we are still trying to explore. So you probably will hear a lot of things that are not certain at the moment. So as astronomers, my goal is really trying to understand how to kind of differentiate the two populations with the latest observation from James Webb Telescope. So given this kind of strong overlap, there's a kind of paradigm shift, that try to just combine both types of objects together. So why do we have to distinguish them if we don't know how, right? So now we basically call them as exo worlds. So they're all kind of worlds with slightly different masses. They're definitely not stars, but we just use the same name to call both types of objects. So throughout my talk, I will use exo worlds to mention these two types of objects. So there are many ways to discover exoworlds. So first of that, which is pretty common method, is called transits. So as many of you probably already know this, the transits happen when the exoworld just has an orbit that just moves in front of the star from its host star. And therefore, when we monitor the host star's brightness, we'll see the brightness is pretty kind of stable until a certain point. So when the exoworld transits the star, we'll see a dip. And if this dip is periodic, then we know this must be something that is orbiting the star, right? So that's a way that we use to confirm this is a transit signal that is caused by some real objects instead of some kind of artifacts. So this is a way that we use to find exoworlds. But again, for this method, we do not directly see the exoworld at all. All we see is a star, and then based on the star brightness change, we use that to derive the presence of the exoworld. Another method is called radial velocity. So similar to the transits, the radial velocity is also the case where we just monitor the star, stare at the stars for a long time. But this time, we don't only look at the brightness, we look at the spectroscopy. So the spectroscopy is observing the way that all of the photons of the stars are just split into finely spaced wavelengths. And therefore, we can see a lot of lines and absorption bands from the molecules in stellar atmosphere. So we can see the whole spectrum and detailed information about the star. So when the exoworld is orbiting the star, it will have a certain kind of gravitational perturbation to the star, right? So when the exoworld is orbiting the star is also orbiting on this very, very small orbit, right? Orbiting the center mass of the whole system. So when the exoworld is moving toward us, that means that's when the star is moving away from us, right? So when the star moves away from us, we'll see the whole spectrum of the star will be redshifted. But then when the exoworld orbits to the other side of the orbit, the star will move toward us. And this when we can see the stellar spectrum to be blue shifted. So if you see the stellar spectra monitor the stellar spectra for a very long time, you can see the spectrum is being blue shifted and then normal and then red shifted and blue shifted, red shifted, go back and forth. If you can see this kind of periodic shift in terms of the spectra, we will get a sense okay, so this is probably because there's an exoworld that is orbiting the star. But again, similar to the transits, we do not directly see the exoworld. Again, we use the stellar signal to get, to derive or infer the presence of the exoworld. So are there any way that we can directly see it? And yes, so that is a method that I am using for my research. It is called direct imaging. So it's simple by name. Direct imaging is you can directly image the exoworld and the star, right? It's simple. But in order to get this image, it's definitely not trivial. So astronomers spend their kind of effort, a career and several decades to make some technology that can make this kind of direct imaging technology happen. So what it means is at the beginning, you can see this is a star from the image, right? The star is really bright. But if I tell you there's a planet over here, you probably won't trust me because we didn't see anything from the image. But what we can do is to place a mask in front of the star. So when you place a mask in front of the star, the planet signal will pop out. Right? So that is how we can directly image the exoworld. So this is the only method that we can directly see the exoworld from the image, and this is different from the transits and radial velocity. And here I would like to show you some kind of real data from the direct imaging. So this is a real planetary system called HR 8799. And at the center, there's a star, and you cannot see the star very well clearly because there's a kind of circular mask, which is a coronagraph. And then you probably will see 4 planets, right? There are 4 planets near this star, and you can see that only after you place a coronagraph. And if you can spend a longer time to monitor this system, this movie is created by using like real data collected across like over 10 years. So by combining all of these kind of images obtained across 10 years, you can sort of get like the orbit of each exoplanet. You can basically see like they're real. They're really kind of orbiting their host stars. So the HRA 799 is a case where like we can only see the exoworlds when we kind of place the coronagraph. And the reason is, again, because the exoworld is so close to the star, so that's why like you want to block the stellar light, right? But if you can, like we can imagine, if we just place the exoworld on gradually wider orbits, there's definitely a certain point that the stellar radiation will have negligible impact on the exoworld. So at a certain point, we don't need the coronagraph anymore, and we can still see the exoworld. So that means the exoworlds on very wide orbits can also be like directly imaged even without the aid of coronagraph. So is that possible? The answer is yes. So this is an example of the exoworld discovery made through like a program that I will mention in a few slides. So the system is called Coconut 3. It's different from the Coconut 2 I mentioned earlier. So we can see like this is an image of a patch of the sky. And this bright star is a host star, Coconut 3A. And here I use another kind of blue circle to mark another very, very red tiny dot. And that is Coconut 3B. So we think the Coconut 3B, this exoworld is actually orbiting this star. And the whole system is like, this exoworld is on a very wide orbit. It's about 2,000 AU. So if you take a look at this kind of HRA 799 movie again, you can see like the scale says 20 AU, right? So the Coconut 3 is basically like has an orbit that is like 2 orders of magnitude wider as compared to the HRA 799. So maybe the question now is like, how do you know this object is kind of like orbiting the star at all, right? And one of the strong evidence that we have is that we have some kind of information about their motion. So this is called proper motion. So we have measured the motion for all of the stars and objects in like this neighborhood. And what we find is that the Coconut 3B and Coconut 3A has the same motion with similar, like, basically everything's moving in space, right? So they have the same space motion with same consistent speed pointing toward the same direction. Well, the other objects in this field, they have different amount of speed or space motion pointing to very different directions. And also the 3B and 3A are at a similar distance. So why this kind of common motion will indicate they are kind of associated? So probably we can take a look at this kind of short video that I took from Pinterest. Maybe some of you also saw that from like TikTok. So what it means is like at the beginning, you can see the sun is at the center, and we have 8 solar system planets. So maybe most people think like when you discover a planetary system, you should see the planets just orbit the sun and the sun is stationary. But the fact is everything is moving in space. So the sun is moving in space, and all of the planets that orbit the sun are also kind of moving in space. So at a certain point, if we just try to measure the motion of all of the planets and the sun in this image, what we should get is like the sun is moving toward this direction, and all of the planets will also move toward the same direction with sort of similar speed. The only difference is that the planets also have some kind of tiny speed that is kind of trying to, for them to orbit the sun, right? But this kind of orbital motion is very, very small as compared to their space motion. So therefore, this means if an exoworld moves together with the sun or with a star, and if they have the similar speed, if the motion points toward the same direction, and if both objects are at the same distance, then they're very likely to be bound together. Right? So following this kind of idea, we can imagine like we probably can find a lot more kind of co-moving pairs in the universe. right? So if we can find some kind of two objects that are moving together in space, and if one of them is an exoworld, then we find a new exoworld system. So that means, ideally, we want to get some kind of real science data that allow us to create a movie like this. So imagine, again, this is just not a real data. It's just a movie for demonstration. Imagine like the sun is at the center and everything is kind of moving, right? And we should have the real science data that describes where each star are at a certain time and then how fast they're moving. So at a certain point, you probably will see like for example, they're like a pair of objects that are moving toward the same direction, right? They are like form a body system. They just move together. We want to find more, like many of these body systems. We want to find all of these kind of co-moving pairs. And from all of these co-moving pairs, we can then try to investigate how many of them have exoworlds. So this is really a starting point for us to do this kind of dedicated exoworld search. So do we have this kind of real science data to create, for us to create a movie like this? And sort of, yes. So we are kind of like astronomers, we're kind of using telescopes to kind of map the sky, right? And there's some kind of large programs that use several large telescopes that kind of keep mapping the whole sky night by night over years. So on the left, I list kind of 3 representative digital sky surveys that exist basically 10 years ago. So these surveys use a certain kind of telescope. Some are in Hawaii, some in Chile, and also this one is in space. So all they do is they map the sky, they record the coordinates of these objects, many different objects, quasars, galaxies, stars, planets, solar system planets, asteroids. And then from all of this, they also get brightness at different wavelengths, right? And on the right, I show 3 new digital sky surveys that I'm very excited about. So the first of that is called Rubin Observatory, which I will talk a little bit more. It is kind of conducting a survey called LSST. It's kind of getting very deep view of the southern hemisphere sky over the next 10 years. Euclid and Gaia are the space satellites that are also mapping the sky. They're trying to get precise coordinates and brightness. And for all of these kind of surveys, once they get all of the data, they create catalogs, they create publicly accessible images, and that's why we call them as digital sky surveys. And this is an example that we can, people use the real data to create a movie for a certain star. It's a Barnard star, right? It's pretty close to us. So this is for the same patch of sky, but it is combination of maybe several frames that are observed across 20 years. So you can see all of the stars are kind of stationary because they are kind of far away from us. Maybe some of them are galaxies or quasars. But then for this star, Barnard star, it is kind of moving. That's with really fast motion. And all of these kind of images, when we combine them together, we can sort of also kind of draw the trajectory of this star, right? So how fast it is moving toward which direction. So we have this kind of data now with digital sky surveys for billions of objects on the sky. So we can use that kind of data to search for some kind of co-moving pairs. So inspired by this, I conducted a program called Coconuts. So the full name is called Cool Companions on Ultra-Wide Orbits. So this is a program that I developed when I was a PhD student in University of Hawaii, and I was really trying to find a name that kind of echoes the Hawaii culture. And the goal of the Coconuts is really trying to find these kind of new exoworlds that are co-moving together with stars. And I was using the digital sky survey data that are available at the time. So this is already 6 to 7 years ago. So back then, I have all of these surveys listed on the left. So I used this data to search for new exoworlds. So this search is really not trivial. You can easily find millions of candidates, and then you have to come up with some kind of ideas to select the objects that are truly or more likely to be exoworld. And then you get a telescope time to do the follow-up observation and study to confirm they're really exoworlds. So through the coconuts, we have discovered 52 new exoworld systems. So this is like a gallery for all of those 52 systems. One of the things that I want to highlight is Coconuts 2b, Coconuts 2 system. And again, here through this image, you can see the whole star is this bright star. And the Coconuts 2b, the planet, is really far away. It's about 6,000 AU. It's that kind of red dot. So the whole kind of system is only 10 parsec away from us. So when it was discovered back in 2021, it is actually the closest exoworld that we have discovered through direct imaging. And then some people made this kind of card to record the properties of the Coconuts 2b. And our discovery hit the press release, and there's some one of the YouTubers that's kind of trying to advertise our discovery. And this plan is also made through a national exam for a Dutch National Institute. So what's next? So my next goal is really trying to expand the Coconut survey by using new digital sky surveys that are being available right now and trying to do a dedicated search for exoworlds and trying to find more exoworlds with lower masses, colder temperatures, maybe more extreme properties as compared to everything that we have known so far. So one of the biggest kind of resource that I'm trying to use is called Vera Rubin Observatory. So this is named after an astronomer, Vera C. Rubin. And you can see it is far away from Rochester. It is in Chile, but we are sort of in the similar time zone. It's here. Well, Rochester is over there. So what Rubin Observatory is going to do is to kind of continuously map the sky that it can observe from Chile. So that is basically half of the whole sky available. And it's kind of collecting data night by night. It will collect raw data, 20 terabytes of raw data per night. So this is a huge data set. So the reason that this data set is huge is because this kind of large telescope of the Rubin Observatory is now able to look deeper as compared to the previous surveys. So the data size here is kind of orders of magnitude larger than the previous survey. So we are kind of really, the astronomy is really now into a big data era. So the issue is really not the availability of the data, but rather how we can efficiently extract the signals from this big data. So I'm now launching a new program. It's called USmile. And the full name is Ultra Cool Dwarf Science with Machine Learning. So what I'm doing right now is to apply machine learning techniques to these big data sets in order to, again, discover exoworlds. And the reason for the machine learning tools is because, for the methods that I use for the coconuts and many of my colleagues, to search for brown dwarfs and exoplanets using the old data, our methods are really kind of not scalable. Sometimes you have to visually check the image, hand tune certain kind of criteria. It's really not applicable to these kind of big data sets. So machine learning is now training, and we want to use this kind of scalable method to effectively find more exoworlds from the LSST dataset. And we did found the first set of brown dwarfs. So LSST released its first kind of data release. It's not official data release, but rather what they call is data preview 1. It's a real on-sky data that LSST observed during the commissioning. So they released this kind of data to the community so that we can start playing with the data, get a sense of what the data look like, maybe think about some projects, programs. And the data was released last year, June 30th. And instantly following that, I'm already kind of applying some kind of machine learning techniques to the field, to all of the data that are available from LSST DP1. So what we found is shown by the red and also blue stars in these images. So these are the three fields that we were kind of interested in, the RA and DAC, and we show kind of gray circles or everything that pass certain kind of quality cuts with the LSST and the stars of what we found. So this is the first set of brown dwarfs that we found from LSST using machine learning. This is something that we are pretty excited about. And the next goal is really trying to apply the machine learning to the next LSST data release, which is somewhere summer this year. So they call DP2, Data Preview 2. And finally, they will have a like official data release maybe next year or another year or so. So I not only find exoworlds, I also try to study and characterize the properties of these exoworlds. So to achieve that goal, I use telescopes to obtain their spectroscopy and study like their chemistry and physical properties. So so basically, I use both space telescope, which is James Webb, and also a bunch of ground-based telescope. So the James Webb telescope is kind of a big deal right now for astronomy. So it has a diameter that is 6.5 meter. It is in space. And I make a gallery for some kind of cool science that the James Webb has enabled over the past few years. So it has yielded some kind of exciting results for like galaxy cosmology, stars, Milky Way, like planets, solar system, like all kinds of astronomy fields. I also use Gemini, Keck, Magellan, like some kind of ground-based telescopes, large and small, trying to study these exoworlds and their host stars. So maybe you have a question, it's like what the exoworld spectroscopy really looks like, right? So this is like a picture of the exoworld spectroscopy taken by James Webb Space Telescope. So it is really the first time that we can see this spectra across this wide, broad wavelength range. So this is spanning from 1 to even over 15 micron. So all of this data, like not all of this data are easy to observe from the Earth because we have the Earth's atmosphere. So given that the James Webb is in space, we can get all of this data with very, very high quality. And this exoworld is called VHS like 1256b is like a phone number. It's here. It's orbiting the star. And again, this is an example like where the exoworld is kind of far away from the star, so we can see it even without the coronagraph. So from the spectra, you can see there are a lot of wiggles, and different wiggles are caused by different like atoms or molecules in the exoworld atmospheres. So some are caused by like water, carbon monoxide, methane, or even clouds. So all of these wiggles are kind of telling a story about the exoworld properties. So my goal is really trying to study these wiggles in the spectra to understand like the properties of the exoworld atmospheres. So here I want to give you some kind of quick examples of like what we can learn from the exoworld atmosphere. First of that, we can get a sense of chemical composition. How much water are there? How much methane are there, right? So this gave us a sense of like what these atmospheres are composed of, whether certain atmospheres is potentially habitable. Second, we can study how fast the exoplanets or exoworlds are kind of like rotating with respect to their own spin axis, right? So this is a spin of the exoworld, how fast they're kind of spinning. Sometimes we can see a scenario where like the exoworlds is just so close to their host stars, and then they lose atmospheres because of the stellar radiation. So we can see sometimes the hydrogen or helium are escaping from the exoworlds, and this is something that we can study through spectroscopy. And after that, we can also see the signatures of clouds, storm, and aurora from the spectra as well. So how do we kind of extract all of those kind of processes, right? Sounds pretty cool, like we can learn a lot of things, but how we make that happen? So a specific method that we use is called atmospheric retrievals. So this is like a Bayesian data-driven framework. And there are a lot of like technical details that I like on purposely make them like dark. But what we do are actually like we fit into the exoworld spectroscopy into the retrievals, and all we get is some kind of constraints to different properties, chemical property, physical properties of these exoworlds. So I feel like maybe it will be better for me to show you a movie about like how the retrievals are actually doing. So again, we're basically trying to compare data with models and then trying to find the best fit model and use the model parameters to describe the exoworld. So at the top panel, this is a real observed James Webb spectrum of an exoworld. And later, you will see 3 curves in the top panel. The top curve, or the curve in orange, is what you probably want to take a look. So that is like a model spectrum. And our goal is to make sure that model spectrum can fit the data well. through some iterations. At the bottom, there's some kind of panels. They're like knobs that the retrievals are playing with. They describe different kind of properties of the exoworld atmospheres. So you can see like the top panel, the orange curve or the curve on the top, you can see it is trying to fit the observed data, while everything else is trying to kind of move a little bit, and until finally you get a best fit in the orange model, right? And then here it tells you some kind of thermal structure about the exoworld, atmosphere, composition, everything else. So for this specific exoworld, so this analysis of what I did recently, and what we learned, just briefly speaking, is like we find for this exoworld, its atmosphere is likely composed of like Apache clouds. So 90% of the atmosphere is covered by very thick clouds composed of silicon and magnesium. And 10% of the atmosphere is composed of thin clouds with sort of similar composition. But the cloud thickness is very different. So that's how we can fully understand the observed data over that wavelength. So with all of this being said, I want to just stop at this slide again, trying to remind you about the true diversity of these exoworlds. And maybe somewhere in the future, if I have a chance, I probably will be able to tell you more about like what we can learn about the specific properties of these exoworlds. And with that, I will just stop here and ready for questions. Go ahead.
Is there any way to detect magnetic fields for the planet?
Sorry.
Question.
Is there any way to detect magnetic fields around any of these kinds of planets?
Yes, there are. Detecting magnetic field is really hard for exoplanets. Sometimes you have to trace certain ions in the exoplanet atmosphere. You can see some kind of different velocity of a certain ions. And again, this can be obtained from spectra, yes. But it's hard to like make sure your data definitely mean this is magnetic fields. Because magnetic fields is complex. It's something like if you ask an astronomer what is magnetic fields, most of them cannot answer very kind of confidently. This is some kind of complex properties. But yes, this is observable.
I have two questions that are perhaps related. So in our solar system, Jupiter and Neptune and Saturn all emit more energy than they receive from the sun. Are you relying on that for detecting the exoplanets without the masking?
Exactly. So we call those planets as like self-luminous planets. So they're internally really hot. Yes.
And then I was thinking about the second chart, but you brought it back up again at the end. So on the side of the chart with the frigid world, the coconuts, the bulk of those are large mass planets.
Yeah.
Is that an artifact of the detection that we're able to detect the larger ones, and there might actually be a population of smaller ones that we just don't know about yet?
That's a great question. I think that's probably true. So it's like right now you can see like basically we have nothing here at the top, like bottom right corner. So that's really like the boundary of the detection limit right now. But I think with, for example, RSST, we'll be able to find probably lower mass like analogs of coconuts to be.
I think it's fascinating what you've found out so far. I look forward to hearing more.
Yeah, thanks.
I was telling some children about exoplanets, and one of them asked me a question, which I will ask you. The child said, "You're always talking about solar systems where there's a hot star with cooler planets going around it. Is there ever a cold star with hot planets going around it?" And I thought, it doesn't strictly violate the laws of physics, but I'm not sure how that would happen. Is there some way it might happen that you would find it?
I think usually children's questions are the hardest ones. I would say,
Giant, diffuse, cool red dwarf with objects around it that somehow collapse and get hotter.
I think the tricky thing here is like sometimes the mass and temperature are kind of correlated, right? So it's like in order for an exoplanet to orbit some kind of more massive objects, the central target like object tend to be more like hotter. I cannot quickly find some examples where some hot objects orbit cold ones. I do know some examples that cannot answer your question. I do know examples where larger objects orbit smaller ones. So, for example, we can find gas giant exoplanets that orbit white dwarfs, right? So that are cases where people observed or detected recently. So yeah, but white dwarfs are pretty hot as well. So it's kind of hard to say. Yeah, yeah. But I will keep that in mind and see if I can find anything like that. That sounds pretty interesting.
Question about orbits. You show all these orbits as circular. Aren't most exoplanet orbits very eccentric?
Yes. So yeah, most of the exoplanets have eccentric orbits. Like also brown dwarfs also have eccentric orbits. So yeah, so it's kind of hard to have like pure circular orbit for sure. Yes.
Do any of these techniques detect planets that are not associated with a star, that are just drifting out between stars?
That is a big topic that I'm studying right now. Those are called free-floating planets. So there are a bunch of exoplanets that are just freely floating in space. They have no host stars when they are observed. We don't know why. So their masses could be like only several Jupiter masses. We found a bunch of them from like many different star-forming regions. It's possible that these planets are initially formed within a planetary system and then ejected outward, or probably they form like stars, right? So it's like when they were born, they were only just several Jupiter mass like brown dwarfs, and they're just freely floating. Yeah, so this is kind of relevant to the question I mentioned earlier. Like it's like how to distinguish brown dwarfs and exoplanets. So I'm now having like a nearly 60 hours of James Webb program that is trying to observe exactly this type of objects. I think we have another question here, probably.
For the looking at proper motion, how long would a LSST survey have to work so you could see proper motion? Is the precision of the coordinates so much that you don't need much time, or do you really need some time?
Yeah, so for the proper motion, typically really depends on how fast the objects are moving. So I would say for the LSST, it will operate for next 10 years. So I think like given this time span, it's definitely possible to get a proper motion for the bulk majority, like almost everything. And like beyond the proper motion, we can even get the parallax. So yeah.
Any other questions? Any questions?
When we first started to see radial velocity planets, we found a lot of planets in the upper left-hand part of that diagram. And it prompted a lot of discussion about, did these planets form there, which is a little odd. You would think they would be more terrestrial with gases going out to the condensation limit.
Yeah.
So the discussion centered around, do they migrate? Have we learned any more about migration of planets and these things, and maybe ejection of planets from those systems?
Yeah, so at the top left cluster, these are called hot Jupiters, right? So, and these hot Jupiters are so close to a star, they're so massive, exactly as you mentioned. So one of the popular theories is a high E migration. It's like they have probably high eccentricity that cause all of these objects to have a certain kind of point where they're close to a star and then get captured, and then they just are left in a closer orbit, like circularized with time as well. So that is one of the kind of a typical scenario to explain their existence nowadays. the high E migration. Yeah.
So Tony was asking, what are the most extreme objects found by coconuts?
I think the Coconuts 2B is the most extreme ones because it has really like far orbit, like wide orbits compared to stars. It's really at the top right corner. It is also like the closest to directly image exoworld, and also it has the lowest mass as compared to all of the like Coconuts discoveries. Yeah.
Someone else's question made me think of this one. Is an Oort-like cloud thought to be a common structure for other stellar systems? And in that case, are the frigid world objects inside of that orbit?
It really depends on also the mass and temperature of the central star. So if if we're talking about the solar type stars, then probably they have some kind of overlaps for the frigid world. But the thing is, like, it's kind of hard to observe the Oort clouds for exoplanetary systems because it's really kind of hard to see the signatures.
Oh yeah, we can only model it
Exactly.
at this point. Yeah.
So yeah, not to say the exoworlds, yes.
All right. Thank you.
Nothing on Zoom yet? Thank you very much. That was a terrific
Cool.
talk.
All right. Thank you.
And that concludes our meeting for tonight. Thank you for coming, everybody. And thanks for the Zoom folks for being on Zoom.